Vibration data is typically collected using an accelerometer, which converts vibration to an electrical signal by use of a piezoelectric crystal. We mount the accelerometer as close to the bearing as possible to capture all high-frequency noise from the bearing, as well as any other components connected to the machine shaft. The data collector records the raw data in a time waveform, which is a graph where amplitude and time are both represented. It is important to remember that vibration isn't typically the cause of a problem, but rather a symptom. The amplitude of vibration, shown in the time waveform, can be represented in three different parameters. Displacement, which is overall movement of the shaft measured in mils. Velocity, which is the max speed of oscillation measured in inches per second. And acceleration, which is the rate of change in velocity, and it's measured in Gs. These values can be represented in three different ways as well. Peak to peak, which is the amplitude from the highest peak in the captured time waveform to the lowest peak. Peak, which is the maximum amplitude from the center of the time waveform. Or RMS, where an average is derived from the overall time waveform. In a simple sinusoidal wave, RMS can be calculated at peak times 0.707. Where this matters is in comparing data to other sources or severity charts. You need to know you are comparing apples to apples. The amplitude measured parameter will be listed. Remember to look for it. Here are some examples. The final severity chart shown is the one we use for Accurex. It is based on the ISO standards and sorts machines by the horsepower of the driver and structural rigidity of the mounting. Each system has its own vibration frequency, and depending on the amplitude, that frequency will identify any issues. On a more complex machine, you can see that the sine wave produced is anything but simple, and would be difficult to analyze. Unless we were to separate out the individual frequencies and represent them as their own function on a different kind of graph. This is where the FFT comes into play. By sorting out individual frequencies, we can easily identify each source of vibration and see its individual effect on the overall vibration of the machine. So again, the FFT takes a complex waveform, sorts out its individual frequencies, and presents them on the FFT, which is a graph showing amplitude versus frequency. So going back to earlier when we discussed the different parameters used for measuring amplitude, each one has their strengths and weaknesses in showing this on the FFT spectrum. As you can see here, this chart shows that displacement, which is the stress indicator, will show very well at low frequencies, but not at high frequencies. Acceleration, the force indicator, shows at high frequencies, but not very well at low frequencies. And velocity, known as the fatigue indicator, will show okay at high and low frequencies, but also has the best response across the middle of the spectrum. When we are analyzing data, we analyze the frequency to determine the source of each vibration on the spectrum. Then, we use the amplitude to determine the severity of the issue, if there is one at all. Another important factor to know when viewing the FFT spectrum is the variables that go into constructing it. First, there is the bandwidth or frequency span of the spectrum. In this example, we can only view data out to 600 Hz. If there was a vibration present at 610 Hz, we wouldn't see it here. There are also a set number of lines of resolution. Each line of resolution is a potential position to show a vibration at a specific frequency. If your resolution is set too low to separate peaks that are very close in frequency, you will only see one peak on the spectrum. By using the sum of the squares method, we can assign an overall value for the vibration present across the entire spectrum. This overall value is used to quickly identify change. By consistently collecting data over time, the overall values derived from the spectrum are used to build a trend plot. When the trend breaks the set alarm limit levels, we know it's time to take action and begin further analysis.